The article Kindergartners as Sense Makers focuses on how students from diverse backgrounds and various learning experiences, whether that be children who have attended preschool or daycare or children where this is their first time experiencing school, all come together in the same shared space. Regardless of children's diverse backgrounds, previous learning experiences, or first-time learning experience, this article highlights that it does not matter, as children are born natural problem solvers and naturally have the capabilities to have genuine mathematical sense-making. Through introducing and focusing on identifying and writing numerals, shape attributes, patterns, and counting by ones, twos, fives, and tens allows for students to engage in problem-solving and sense-making. The article introduces one way that engages young students in problem-solving and sense-making is through word problems. By providing young children with a variety of tools such as manipulatives and counting tools such as stickers, tokens, blocks, buttons, etc., aids students' abilities to approach a word problem that makes sense to them, furthering their ability to then make sense of the word problem. When children can choose and have autonomy in the way that they are able to solve a problem, it fosters their enthusiasm, desire, and agency in their learning and abilities. Overall, the purpose of this article is to show how young children can and are able to solve and make sense of word problems using mathematical sense-making when provided with tools, structure, instruction, and support functionality by providing a variety of counting tools such as stickers, tokens, buttons, blocks, etc., and allowing students to choose supports their problem-solving skills and mathematical sense-making. This directly shows students saying the counting sequence, one-to-one correspondence, and counting objects. For example, the article shows a direct model of students counting each item one at a time. First, they use blocks to represent 5 marbles by counting each block to reach 5. Next, they create a pile of 3 blocks, counting each at a time. Once the 2 piles are created, the student starts back at 1 and counts all 8 blocks. This demonstrates one-to-one correspondence, each block equals 1 marble, cardinality, after counting the total, they state the final count, 8, and counting objects to represent quantities. Lastly, in the article, it mentions the discussion of counting strategies such as counting on, which shows students using the cardinal value of one quantity and continuing the count to find a total, demonstrating a more advanced understanding of the difference between direct modeling and counting strategies and using different tools. These examples align with the mathematical content of counting and cardinality, showing how children use counting to make sense of mathematical situations and solve problems. This connects to concepts that we learned in class about counting one-to-one correspondence, list, and cardinality. In the article, it shows children counting real objects such as buttons, shells, blocks, tokens, and etc. when solving word problems. In class, we saw where students worked with bears to make sense of quantity. For example, in the lesson, we saw 3 different responses to the question. First, the students showed the students some bears and had them count the bears. Then students counted 6 bears. Then the teacher covers the bear and adds 1 more bear to each side and asks the students to count how many bears there are in total. Child 1 was unable to answer the question of how many bears there are in total, showing that they have not yet fully developed or understood counting cardinality. Child 2 says 1, 2, 3, 4, 5, 6 while pointing to the covered bears, then points at the new bear and says 7. And finally points to the new bear and says 7 and finally says there are 7 bears, showing one-to-one correspondence and an understanding of counting a list of objects, but still does not fully understand cardinality. Lastly, child 3 says 6 while pointing to the covered bears, then points at the new bear and says 7. And finally says there are 7 bears, showing a more full understanding of cardinality. This aligned with the article's description of children progressing from a direct model to more advanced counting strategies. Another mathematical content that I found in the article was cognitively guided instruction problem types. In the article, it mentions how teachers use CGI problem types such as separate, star, unknown. Students were given separate star unknown problems which required them to be able to determine an unknown starting amount after a quantity is taken away. It was found the students used primarily 2 types of strategies, direct modeling and counting strategies. For direct modeling, many of the students started by directly modeling the problems by using physical tools such as bears. Another drew a picture and another used the double 10 frame with cubes. As the students progressed, some students shifted to using more advanced ways such as counting strategies. Students use number lines, their fingers, or mental counting. This connects to the concept we learned in class about solving additional problems with a star unknown. We learned that for young children learning how to solve addition problems with a star unknown, that most children often begin and start with using direct modeling. For example, with the problem 4 plus 6, they would have to count out 4 things first, or use their fingers, then count out another 6 things, or use their fingers to count the total amount of things. For count 2, students would count up from the first number. For example, 5 plus 4, they would say 5 while potentially pointing to objects. Then the child would say the next 4 numbers, either 5, 6, 7, 8, 9, most likely using their fingers to get the total. For students who use count on count on larger, they usually know to start with the larger number and then count on from there. For example, if it was 2 plus 3, they would start with 3 first instead, then add 2 to get the total. Lastly, to make a 10, we want that students use a combination of 10 for easier addition. For example, for 8 plus 7, they would break apart the 7 into 2 plus 5, so that a 10 could be made from the 8 and the 2. So the total is 10 and 5 once to get 15. In the article, kindergarten students use similar strategies such as direct modeling, manipulatives, counting on from a number, or using fingers to solve separate start unknown problems.
So for our activity overview, this consisted of 2 kindergarten classes where they connected 8 lessons. These lessons were conducted through cognitive guided instruction problem types. During group instruction time, a team member would read a story problem aloud and provide a written copy to the students. Students were allowed to problem solve any way using mental strategies, fingers, number lines, reckon racks, cubes or bears, 10 frames, paper and pencil, etc. Students then, after solving the problem, would have to explain their strategy. In the article, the worksheet was intentionally kept extremely simple. Each student received a small paper with only the text of the word problem on it. No pictures, no number lines, no nothing. That would suggest a specific strategy. The teachers wanted the worksheet to serve as an anchor for the story, not as a step-by-step guide. This approach is very consistent with CGI because it allows students to choose how they want to represent the problems. Students were instructed that they could solve the problems in any way that makes sense to them. After working, they were expected to show their thinking and explain it to their group. The worksheet was intentionally open-ended so that strategies would come from the students and not the teacher. This supported genuine sense-making and allowed each student to approach the separate start unknown problems using tools and methods that fit their individual thinking. For the first worksheet, the problem was, Molly had some pencils. She gave 3 to Jacob, and now she has 6 pencils. How many pencils did Molly start with? While Jacob was waiting for his friends, he created this picture to model his solution. He wrote how many pencils that Molly has now and answering with 9 to start with. But as we look at the picture, we can tell that he did not put all the pencils and that there's only 8 in the picture. The next one is Julio. Julio had the exact same problem, but Julio solved this problem by using first a number line on the table. He pointed at 6 and then 9, which he saw that was 3 more than 6, so he figured out his answer was 9. He then decided to illustrate a picture of the number line to show how he solved it. And then for our last artifact, during Julio's post-assessment, his question was, Bridget had some orange slices. She gave 2 to Gabe. Now Bridget has 4 orange slices. How many orange slices did Bridget have to start with? Julio used a picture representation to solve the problem. He wrote the equation and drew the orange slices to match. Then he counted all the slices, writing the numeral 6 for the answer to his equation. Then he drew the orange slices to represent how many slices Bridget had to start with.
Based on the article, kindergartners face real hurdles with separate start unknown problems. These are problems where you know what's given away and what's left, but not how many you started with. And that missing starting point is the big challenge. The first major difficulty is the inaccessible starting point. Students can't see or touch sum, so they can't physically represent it right away. Because of this, they often default to trial and error, just guessing instead of using a strategy. This leads to strategy instability, where they might move back and forth between more or less advanced methods as they try to figure it out. Students also tend to be highly tool dependent. They need something physical like cubes or fingers or drawing to anchor their thinking, as these tools make the abstract concepts of cardinality, the how many-ness of a set, concrete. But picking the right tool isn't automatic for children. Finally, there's the challenge of verbalizing abstract thinking, explaining what sum means or how they found the missing number is really tough for young learners, often because they are struggling to describe the cardinal relationships between sets and creating a gap between the story problem and the math. Now, what does the article conclude? Despite these challenges, the research shows that young students are fully capable. With the right support, they can move past guessing and use real strategies like direct modeling and counting on. A huge part of that success comes from tool choice giving, so they can find a pathway that makes sense to them. The article gives clear instructional must-dos. First, embrace complex problems early and don't shy away from SSU tasks. Second, provide a variety of manipulatives to encourage different approaches. Third, structure both small group and whole group discussions so children can hear and compare strategies. Fourth, use questions like why did you start there, and can you show me us another tool, instead of giving answers. And lastly, validate all student strategies to build confidence and flexibility. This creates classrooms where every child sees themselves as a doer of mathematics. Students develop perseverance, flexibility, and the ability to learn from others. The teacher's role shifts from providing answers to starting discussions that highlight students' thinking and strategic choice. So this study proves that even our youngest learners can tackle tough problems not by simplifying the math, but by strengthening the instructional support around them. When we give them tools, time, and talk, we don't just teach them math, we build sense makers.